Welcome to Industrial PLC Applications. This video is part of a series introducing you to industrial automation and preparing you to program programmable logic controllers. Our focus will be the Allen Bradley Micro 850 PLC and the connected components workbench programming and integrating software. In this lesson, we'll take a look at one of the fundamental building blocks of industrial automation, relays and relay logic. Welcome to our video series. My name is Alan, and I will be your host throughout the series. If you have questions, please leave them in the comments section, and I will attempt to answer them by creating more specific videos. This video's objectives are to assist you in identifying relay logic-controlled automation, explaining relay operation, and identifying different relay applications in industrial automation. Let's review what we mean when we talk about automation. Wikipedia defines automation as a method of operating or controlling a process by highly automatic means via electronic devices, reducing human intervention to a minimum. Basically, this means that automated machinery and systems will function automatically without a lot of manual intervention or continuous input from an operator. Basic automation can control more than stopping and starting of a machine. It can control speed, volume, flow, temperature, pressure, production progress volumes, and a whole lot more. But automation's largest role is the sequencing of machine action. And this is only scratching the surface. To understand automation, we must familiarize ourselves with the first, widely adopted, electrical method of automation that uses electrical relays and relay logic. Let me turn this section over to my colleague Nancy.
Thanks, Alan. I'm Nancy, and I will be assisting Alan through the series. Now, let's look at electrical relays. Relays are electromechanical devices that act as controllable switches. When a number of them are used to control machinery, we call their sequential operation relay logic. Relay logic is defined as a form of automation where machine and process operation is controlled and monitored using electromechanical switches called relays. In the early part of the 19th century, simple telegraph systems were being developed. But there was a problem. Messages could not be sent over great distances. In the 1820s, before Edison's work with the DC generator, telegraph systems used voltaic piles, essentially early batteries, or static electricity to send their signals. These signals were weak, and as the distance increased, the available voltage dropped until the signal became too weak to be useful.
So how did they send a weak electrical signal over long distances like a train route?
Well, Alan, this guy, Joseph Henry, was studying self-inductance. And while experimenting with crude electromagnets, he developed a device that would change electrical communication. The electric relay. Henry realized that his device could be energized by a relatively small local power source and used that energy to close a set of contacts. Those contacts could then control another power source. So instead of trying to push the original weak electrical signal all the way down the line, each station could use the incoming signal to operate a relay and pass the message on to the next station. Just like a relay race, where each runner carries the baton to the next runner. And that's where the name relay came to describe this kind of electrical device. Joseph Henry made the first electrical relay in 1835, and its purpose focused on the railroad telegraph system. Although not likely his original intention, what he invented was a controllable switch, a switch that could be remotely turned off and on, and pass on that change of state to a new electromechanical switch along the line.
Okay, Nancy. Let's take a look at the relay and its basic components.
The largest part is the coil. It's made up of fine copper wire wrapped around an internal metal core like iron. The coil is energized through its own set of power contacts.
When electricity passes through the coil, a magnetic field is produced.
That magnetic field is immediately put to work pulling on the metal swing arm bar, called the armature.
The field pulls the top down, and the linkage portion is pushed outward towards a fixed contact reed until it makes contact, closing a potential circuit.
The contacts that close are often called dry contacts. This is to identify that they are not electrically connected to the coil circuit's power terminals.
When power to the coil is removed, a spring pulls the armature back to its shelf state or open contacts position.
The armature can be connected to more than one set of contacts. Here we see two sets of contacts, one normally open and one normally closed.
Many relays have multiple sets of contacts, allowing for better and more sophisticated control.
Relays now come in a wide variety of shapes and sizes, depending on the current and voltage available. But they all share the same basic components.
That's right. They can be very small solid-state relays on electronics to very large relays capable of handling hundreds of amps. Take this small control relay. This one is a popular size and pin configuration, and it's known as an ice cube relay because of its size and clear plastic housing.
You can clearly see all the parts, including its normally open and normally closed contacts. Do you know why we call them normally open or closed?
Basic automation can control more than stopping and starting of a machine. It can control speed, volume, flow, temperature, pressure, production progress volumes, and a whole lot more. But automation's largest role is the sequencing of machine action. And this is only scratching the surface.
Why don't you explain it for our viewers?
Certainly. Imagine going to the store and asking to look at a relay. They take it out of the box, and you use a meter to check for continuity. Some contacts will cause a beep, meaning the contacts are touching or closed. The others will not, indicating they are opened. Electricians use the term shelf state to reflect that evaluation. Shelf state is another way of saying the de-energized or inactive state of the coil, and therefore the armature and contacts. It is the first concept you must remember about all relays and relay logic. The other concept is that the power that supplies the electromagnetic coil has nothing to do with the power that is tied to the contacts. It can be the same, but because that is a control's decision and not a standard, you treat them differently because the electromagnet is electrically isolated from the armature and changing contacts.
Well, Joseph Henry had no idea what he started, because relays were quickly adapted for industry. Relays allowed industrial plants to make use of the electrical grid Tesla helped to create, and from that helped Henry forward with his new automation ideas. Automation expanded the capability and efficiency of machinery, since they removed the necessity of manually opening or closing circuits. But not only did Joseph create a remotely controlled switch, his little relay was able to store a single unit of data, and that led to being able to count and stored values, and later even to control operation with timers.
Yes, but all this new complexity had to be standardized, and this led to the development of relay logic and relay logic schematics.
Yes, Alan, but that subject deserves its own video.
Absolutely. Until next time, thank you so much for watching. And if you want more content, click the subscribe button or drop a comment below. Thank you again and take care.
Up next, relay logic. So for Alan and me, hasta la vista until next time.